This third and final video for Lab 7, we're going to cover the binomial distribution, which describes the number of successes in a fixed number of Bernoulli trials. So now we're saying, okay, I'm going to do n Bernoulli trials, and I want to know what's the probability that exactly k of those are a success. And so you can see the probability of this is a little more complicated. This equation is a little bit of a mess. So now we are going to use R to calculate this. Just like the normal distribution, that's a little bit complicated to calculate by ourselves. So we're going to use a function to do both the normal and the binomial. So let's get into just a simple example. Well, simple, that's up for debate. But what I will say is I'll break it down so we can have R do all the heavy lifting. So, okay, the deductible example. The probability of someone exceeding their deductible is, it's actually 0.3, sorry. The probability of someone not exceeding the deductible is 0.7. So let's correct that. Okay, and now we're saying, okay, I got 8 people I'm sampling. Maybe I'm a business who has 8 employees, and I'm providing their own insurance now, and I need to know, like, how do I have a contingency for 5 people exceeding their deductible? Maybe I don't want to pick a budget for more than 5 people exceeding their deductible. Oh, that would be 3 people. So 5 people don't, that means 3 people do exceed their deductible. So we're looking at this formula up here. It's a fixed number of trials, and if you ever hear fixed number of trials, Bernoulli trials, and we're finding the number of people that exceed or have a success or a failure, that's a binomial. And so n is the number of trials, k is the number of successes we're interested in, and p is the probability of success. If we just put those in, it calculates there's a 25% chance of only 3 people exceeding the deductible, 5 people not exceeding their deductible. Okay. And so let's look at the plot for this. Notice the binomial distribution only has 8 outcomes, 1 through 8, and it looks a little bit like normal, but it's not symmetric, and it's definitely discrete. So we can see this is a unique distribution that we have to consider differently than the previous two. So here's an example. What's the probability that 2 out of 8 exceed their deductible? Well, we'll copy this, and remember, 8 is our fixed number of trials, k is the number of successes, which is exceeding their deductible, that if all but 2 out of 8 exceed their deductible. That would be a lot of failures. So six people. Oh, only 2 people. Sorry, 2 not exceeding your deductible is a success. So we're looking at 2 successes in this case. So that's a little smaller probability. So 6 people exceeding the deductible is a 1% chance. Okay, and what about 8 out of 8? 8 out of 8 not meeting their deductible would be 0 people having success. What's the probability of that? Super low. That's practically 0. If you see this, e -5, that means 4 zeros, a point. This means 0.1234, and then a 6, if you're not familiar with scientific notation. Okay, so I'll let you do 14, we got 40 cases that an insurance agency is interested in, and we're looking at the most likely number that people would be to expect to exceed their deductible. So what you could do for this one is plot this, but change it to where we're looking at 40 people. Oh, but you haven't used vectors. Okay, so we're looking at the size being 40, and we're looking at 1 to 40. That's what this means. If I have 1 semicolon 40, that's how many different cases we're going to look at. And if we plot that, that's the distribution for 40 cases. So what looks like the most likely number in that? You guys can guess or like get a good approximation of that. Or if you're fancy, X is your number of your probabilities. So you would just look at the max of X. No, that would just give you the probability, the maximum probability. So disregard that. That's not going to help. You guys will have to look at the graph to answer this one. All right, so this is helping us interpret, like, what does this distribution tell us? Okay, so there is just a little bit of conditions that need to be met in order for us to really have this distribution apply to a situation. Like I mentioned, the number of trials needs to be fixed, and the probability of a success or failure is the same. Oh yeah, and each trial has only 2 outcomes, success or failure. And then lastly, the trials must be independent. So let's look at this example. Okay, about 30% of people who smoke develop severe lung cancer, if you just look at the general population. And so now let's consider, suppose you have 4 friends, all of which who smoke. All your friends smoke, and are the conditions for modeling a binomial distribution satisfied? Can we look at the situation according to a binomial distribution? So we have to check, are the fixed number of trials, is the number of trials fixed? Yes, check, because you have 4 friends and we're looking at a situation of just 4 people. Each outcome is a success or failure. Well, either they get cancer or they don't, so yes. The probability of success is the same. Not so sure, but according to the information we have, we could say, yeah, it's about 30% for each people. They might be pre-existing conditions, but if we don't assume that, we can pass that test. Are the trials independent? Are your 4 friends independent samples from a general population? I would say no, because your friends might have similar habits or like might influence each other. So technically we can't consider this a binomial distribution, but if we want to kind of overlook this last one of them being independent, well, we can still model it. This is still an interesting problem, right? So if we assume that getting lung cancer satisfies these conditions above, what's the probability of your 4 friends, exactly one of them, developing lung cancer? Aha, this is a binomial distribution. So let's go reuse some of our work. That's the key to doing a lot of these problems, is figuring out what are your variables and then have R do the rest of the work. Okay, so N is the number of trials. We got 4 friends. K is the number of successes we want to consider. Well, in this case, success is getting cancer. So we're looking at 1 friend. And the probability of getting cancer is 30% if you're a smoker. And so what is that probability? 41%, not too good. Okay, so that's a pretty interesting thing to be able to compute. And I'll let you guys figure out what is the probability that 1 or more will develop lung cancer. You'll have to calculate the outcomes for 2, 3, and 4. And what's the probability that no one will develop lung cancer? So yeah, and then I think you can do the last one on your own. Definitely check with me if you have questions, ask questions in class, or message me if any of this is confusing. I really do want feedback on these labs so I can make them better. Make sure you're understanding this material. I want this to be a tool for you to understand these ideas. So yeah, try the bonus if you're feeling good or want to challenge yourself. All right, thanks. See you in class.